In this lecture, I want to talk to you about the difference between dynamic and static types. Types have many uses in programming languages, but perhaps the most important is to enable the compiler to compute offsets. This is a standard feature, for example, in C, if I have a structure with multiple fields, then when I access a field of that structure, it's important that I figure out where the value corresponding to that field will reside in memory. Another important use of types is to determine what operations may be performed on a particular value. On line 3 here, you can see a valid line of Java where I'm trying to compute the difference between 1 and 2. But on line 4, you see something which is clearly not Java. I'm trying to compute the difference of dog and cat. Subtraction is not a valid operation on strings in Java. So these are two different uses of types. When we think of types, we most often think of type enforcement. That is, what are the types doing to me as a programmer? How are they constraining me? And the constraints come in two different styles. So there's a static constraint. These are types that are tracked by the compiler. And there's also dynamic constraints. These are types that are stored with values in memory and then used when an operation occurs to determine whether or not the value supports the given operation. These concepts of static and dynamic are extremely important in computing, and roughly they correspond to compile time, or early in the case of static, and runtime or late in the case of dynamic. So you'll see these terms used in many cases. All three different styles of terminology are used. And it's because this concept is so very important. The difference between the time before a program runs and then once it's running. So if enforcement is so important to the notion of type, what does it mean in C to have a type? Because C doesn't enforce types. So why have them? In fact, in C, the sole purpose of types is to compute offsets in the examples such as the one here. Types in C don't actually enforce valid operations or safety. In languages like Scheme, types are used to enforce safety. So, for example, in Scheme, if you type in the expression that tries to subtract hello from 5, you will get an error. And I'm going to tell you, this is a dynamic type checking error. But of course, if we just type this expression into Scheme, you can't really tell, because in Scheme, the expression is input and then compiled immediately and then run. So how can you tell what's happening? So the solution is to defer the actual operation inside of a function. So if I do this, I can define a function that performs the subtraction. So note, I have not immediately done that subtraction, but I'm potentially going to do it in the future. Note that Scheme has no problem defining that function. It's only when I invoke the function that I get the error. And here we can really see the difference between a static and a dynamic error. So static errors are enforced at the time of definition, whereas dynamic errors are enforced when we actually run the code. So Java, obviously, it's a static language because we do get errors when we attempt to compile code. For example, if I have an integer and a string and I try to compute their difference, I will get an error. But we can also say that Java is a dynamic language, because any error we have in Java in compile time can be converted to a dynamic error by doing some casting. So here I'm trying to compute the difference between an integer and a string. So what I can do is say, well, take this string and treat it like an object. That's anything. And then take that object and treat it like an integer. And as a result, the compiler's happy, but we'll get a dynamic error at the point that this cast is checked. So this is an upcast from B to object, always safe. But this is a downcast here from object down to int. And therefore it is dynamically checked in Java. So when we attempt to run this program, we'll get a class cast exception telling us that strings cannot be cast to integers. So Java is both static and dynamic. We often talk about static and dynamic languages. And as I think you've just seen, this is a bit of a false dichotomy. Nonetheless, in static languages, we can sort of have a different idea of what's happening in a dynamic language. Normally, Java would be considered static. And the reason is that static languages allow variables to have types. And this is definitely the case in Java. So if I declare a variable a to have value 5, if that variable is at type int, then I cannot subsequently assign the variable to hold a string. I'll get a compiler error. This is, of course, like all static errors in Java, something that I can avoid. I can avoid it by using casting. So what I can do here is say, well, take hello, convert it to an object. That's a safe upcast. And then convert down to integer, just as I did before. That's a downcast, which will be checked, however. The compiler will be satisfied. This code compiles just fine, but I'll get a runtime error. In Java, we have the ability to use declarations where we do not specify the type. So this is the var form, but it's important to note that even though we do not specify the type, Java infers a type for the variable. And Java infers the most precise type it can. So here I'm assigning a to be an integer. Java could choose int, it could choose integer, it could choose number, it could choose object. But it chooses the most precise type it can find, and that's going to be int. As a result, when I try to assign a string, I still get a compiler error here. This is not a dynamic error. This is a compiler error. In dynamic languages, variables do not have types. Only values have types. This is the same program written in Scheme, where I've defined a main function that initially associates 5 with a, then it mutates the variable using the setBang operation to hold a string. This is perfectly fine in Scheme. Variables don't have types. Any value can be associated with any variable at any time. Dynamic and static checking both have their place. Dynamic checking is more flexible. It's a little simpler because I don't have to worry about the types of variables. There's less work to do because I don't have to check very much. Those are all great advantages of dynamic languages. On the other hand, static languages have the ability to check more errors at compile time and to avoid certain repetitive testing tasks that are necessary if you don't have type information in the code. They'll also potentially give you a faster runtime. This is one of the main reasons that companies switch from using dynamic languages like Python to using static languages like Scala in their backend, as did Twitter. To conclude, let me make a few comments about static type checking. The first is that static type checking is always conservative. So if I have a function that is always going to return an integer, a static type checker may reject it just because there's some code path, even though it will never be taken, that could possibly return something other than an integer. Static types also may use inference. They don't necessarily require explicit type declarations. In addition, static types may not even be in your program. If you look at Facebook Flow, this is a type system for JavaScript, which puts types in a completely separate file from the JavaScript code itself. The first is that static type checking, oh my God.